So we left off talking about addition to pi star. Most of that addition to pi star that you're going to see is addition to carbonyl groups. That's the majority of arrow pushing where you have your nucleophile add to a double bond. But I mentioned this critically important intermediate for modern organic chemistry or even ancient biochemistry, and that is iminium ions. It is easier to attack iminium ions than it is to attack regular carbonyls. So iminium ions with an N plus are easier to add to than a carbonyl group that's neutral. And so nature often takes advantage of iminium ion intermediates for bond formation. I'm showing you an example of a Knoevenagel condensation, a Knoevenagel condensation, where you don't see any iminium ions in the reactants. You don't see any iminium ions in the final product, but there are iminium ions that are critical for the mechanism of a Knoevenagel condensation. So you need to remember how easy it is to add to an iminium with an N+, or a carbonyl that has a Lewis acid attached for a proton. That's even easier, but those are a little bit harder to make than iminium ions, those intermediates. Okay, let's talk about another kind of catalysis, kind of like forming an iminium ion as a type of catalysis, that's called nucleophilic acyl transfer catalysis. We can add nucleophiles when we're making esters, when we're making amides. There's a special type of nucleophilic catalysis that can occur where we add something special, and in this case that something special is pyridine. That happens to be the solvent for the reaction, but it's not just acting as a base in this reaction. The pyridine solvent is doing more than that. And so let's go ahead and take a look at what that pyridine is doing here in this seemingly simple esterification reaction. So I'll go ahead and draw out the structure of pyridine just to remind you. Pyridine is kind of like a benzene ring where you have replaced one of the carbon atoms with a nitrogen atom. And there's a lone pair that sticks off the side of that benzene ring and can add to things. So if you have a carbonyl group somewhere like an acyl chloride, a highly reactive acylating agent, typically an acyl chloride or an anhydride, a carboxylic acid anhydride, are two very reactive carbonyl groups. The pyridine is more nucleophilic than the alcohol. And it happens to be abundant in this case because the pyridine is the solvent. And so the first step of the mechanism is not having the alcohol attack. The first step of the mechanism is to have the pyridine add in, and it will make this tetrahedral intermediate. We push the electrons up to the carbonyl. Look at that chloride leaving group. It's right there. Got the lone pairs on that O-. Those lone pairs can push out, alkoxide type anions. They can certainly push out this chloride leaving group. What a great leaving group. Kind of think of that as kind of an SN1 type process, an ionization, but that's no regular carbenium ion that you're making. So the next intermediate that we draw in this reaction is the key intermediate here. It's called an acyl pyridinium intermediate. This is a very specific acyl group, acetyl, like acetic anhydride. There's a positive charge on that nitrogen. So this is an acyl pyridinium intermediate, and that intermediate is super reactive right here, super electrophilic. More electrophilic than the acyl chloride was in the reaction mixture. Super reactive. It's going to be super easy for us to attack that carbonyl group now that we have that acyl pyridinium intermediate. Let me just redraw that intermediate down over here. You don't have to redraw it, but that's just the way I chose to depict this. I'm going to draw this acyl pyridinium intermediate, or more specifically acetyl pyridinium intermediate. It's not benzoyl, in this case it's acetyl with a methyl group. And so it's very easy now for that alcohol to add in. That's supposed to be an N right there. It's very easy for this alcohol to add into that acetyl pyridinium intermediate. There we go. We remake a tetrahedral intermediate, kind of like we just had a little while ago. But we're not ready to push out that pyridinium ion. In this case, we want to deprotonate the alcohol before we push out that pyridine group. So let me draw this. BN means benzyl. It's not the same as phenyl. Benzyl is phenyl with a CH2 in between. So we're not quite ready to push out that pyridine group. So when you substitute acyl chlorides, when you substitute anhydrides, you want to deprotonate the alcohol nucleophile. So I'm going to just write the letter B here. Our solvent is a base. The entire solvent is a base, so the conditions are basic. So I'll use the letter B here. I'll take off that proton. And now the lone pairs, I'm not going to show this with my arrow pushing, but now the lone pairs on the benzyloxy group are also helping to push out the leaving group in addition to the O minus. I've got to choose where I start my arrows, but now the lone pairs here on the O minus and the lone pairs here on the benzyloxy group are helping to push out this pyridine as a neutral leaving group. We'll push that right out, regenerate a carbonyl, and that's the mechanism for esterification. When you esterify, and this is a very common transformation, when you esterify with acyl chlorides or anhydrides in the presence of using pyridine as a solvent. Now, some clever person said, well, I don't always want to use a gallon of pyridine as my solvent for the reaction. And what they realize is that if you soup up your pyridine, you can get by with a catalytic amount. Just a pinch. Let me show you a slick derivative of pyridine called 4-dimethylaminopyridine. Let me go ahead and draw that over here. DMAP, 4-dimethylaminopyridine. Here's pyridine. That's the structure of pyridine. And if you put a dimethylamino group on the opposite side at the 4 position, look at that lone pair on that dimethylamino group. You know, that lone pair is donating into the pyridine ring, into the aromatic ring. That lone pair is right there. That's DMAP right there. This thing right here is DMAP. I'll just write DMAP. And again, it stands for 4-dimethylaminopyridine. That's a super powerful nucleophilic acyl transfer catalyst. It likes to attack acyl chlorides. It likes to attack anhydrides, that DMAP group with that lone pair on there. And so it serves the same role as pyridine in the previous mechanism. But notice here, notice you can get by with just 10 mole percent. Not solvent, but just 10 mole percent. And that 10 mole percent accelerates the rate of acceleration by 10 to the 4th. Man, 10,000 times faster because you just put a pinch of DMAP in there because it forms an acyl pyridinium intermediate. Let me draw that acyl pyridinium intermediate. Here's the intermediate that you generate in this case. Really accelerates this acylation reaction. Normally that doesn't matter if you're acylating a primary alcohol. Those reactions are fast, but sometimes you can have tertiary alcohols that start to become hindered, and this can really help you. Right? If you want to get out of the lab in 3 hours instead of 3 days, that might be pretty useful to accelerate your reactions. All right, so that's a nucleophilic acyl transfer reagent. And it's another form of organocatalysis. Okay, so we've talked about addition to carbonyl groups. We've talked about addition to aminoamides. Yes, question?
I had, would it be plausible that the pyridine would attack the alcohol first, and then the alcohol would attack the carbonyl?
No. So the question is it plausible? Is it plausible? And that's a good question. You couldn't possibly know the answer to that. Whoa, what was that multicolor thing? Is it plausible that the pyridine would deprotonate to make a benzyl oxide anion? If you want to run a reaction where you want that to occur, use triethylamine. It's 100,000 times more powerful as a base than pyridine. When we want to make small amounts of alkoxide intermediates in an organic lab, we use triethylamine. If you just want to pull off a proton from some positively charged oxonium ions, pyridine. And that's usually the case. So it's more common it's not common to make benzyl. You'll never make a large quantity of the benzyl oxide anion, even with triethylamine, but pyridine is just not basic enough. You're using pyridine to pull off a proton from some oxonium or ammonium ion intermediate. Yes, question?
Is the 10 mole percent of the DMAP, is that like the max you get, or is that like a point of diminishing return?
It's expensive. So the question is, why 10% DMAP, not 11%, not 12? It's expensive. So if you added 5 times more, it would be 5 times faster. 10 times more, 10 times faster than the 10 mole percent. So you can always add more, but it's an expensive reagent. Pyridine is dirt cheap. Problem is you've got to get rid of the pyridine, and it causes sterility, and there's other whatever. So it's just a cost issue, really. So yeah, I would love to have my reactions 100,000 times faster, but Maybe that's a diminishing return answer to your question. Okay, so we've talked about addition to carbonyls, to iminium ions with a plus on that nitrogen, on an iminium ion. But let's talk about a different type of system. We said it's not easy to add to alkenes. But if you conjugate that alkene to a carbonyl, it's not just a regular alkene anymore. That's not just a regular alkene, it's an enone. I would refer to that as an enone functional group to emphasize the fact that there's a carbonyl attached to that CC double bond. And what you'll find is that there's no problem adding nucleophiles, even highly stabilized nucleophiles. Let me start with this lone pair. I see that kind of an alkoxide. The sodium makes the lone pairs very nucleophilic. And so we can take this central carbon atom here. Let me put a dot on that central carbon. That's the nucleophilic center. That'll now add easily to the enone in this system. And I'm going to push the electrons all the way up into the carbonyl. Here we go. That right there is why that alkene is so reactive. It's not a regular alkene, it's an enone. Boy, that's so easy. It just feels so good to do that arrow pushing. You could have pushed the same arrows if you wrote it sodium plus O minus. The arrow pushing wouldn't be any different. But really there's a sodium-oxygen bond in this nucleophile. So let me go ahead and draw out the next intermediate. I've got this acetyl acetone thing. I've now made my amazing carbon-carbon bond, Na plus. That's not a well-drawn A. There we go. Here's my new carbon-carbon bond. I got to count very carefully here. This is the number one mistake I see people make, is they forget how many carbon atoms there are in this system. And so I'm going to be very careful to note that I don't forget this CH2 right there, because it's easy to forget that when you draw the next intermediate. You're saying, I'm never going to make that mistake. Yes, you're going to make that mistake. That's why I'm telling you, I'm warning you right now that you're going to make that common error of forgetting that CH2 group. We still have that enolate intermediate that we just generated. When we added to that, that's supposed to be a minus charge right there. We just added to that enolate intermediate, and now we've got some proton transfers. I'm not that excited to show you all the steps of the proton transfer. The conditions are basic. If you're making malonate anions like this one over here, the conditions for making that malonate, this initial stabilized enolate, are basic. So I'm going to use the symbol HB because we have to protonate this new unstabilized enolate that we just made. So let me go ahead and write some sort of a symbol here for, I guess this would normally be done in alkoxide solvents. I guess usually ethoxide is a common one. Let me use my red pen here. Let me go ahead and recreate the carbonyl. We'll protonate this. So here's what we have to do for this mechanism, right, where it's a couple things that are left here, is we have to reprotonate the ketone to regenerate the ketone, and we have to get rid of that sodium. I'm going to choose to protonate because proton transfers are generally fast. I'm going to choose to protonate that enolate to regenerate the ketone functional group. And then in a second step, you can pop off the sodium ion that would just be sitting around over here. I'll just draw it. But those aren't the exciting steps. The exciting step is the formation of that carbon-carbon bond under such mild conditions. This is the way we used to make carbon-carbon bonds 70 years ago, back in the 1950s or 1940s, before we knew how to make powerful enolates using LDA, lithium diisopropylamide, before the invention of lithium amide bases. Okay, what are some examples of nucleophiles that are very good? Because what's not obvious here is that you could also, in theory, have added to the carbonyl. You had an enolate, you had a carbonyl. How come it didn't add to the carbonyl? Right? The clue here is that this was a super stabilized enolate where the negative charge was delocalized on 5 different atoms. That was a highly delocalized negative charge. These stabilized enolates, like diketones, when you deprotonate in the middle of a diketone, like right there, that carbon becomes nucleophilic and good at doing these types of conjugate additions. We refer to this as a conjugate addition reaction when you're adding to an enone on the end carbon and not to the carbonyl. We also call these 1,4 addition reactions. And this particular version of a conjugate addition, 1,4 addition, is called a Michael reaction. Usually when we're adding amines or these stabilized enolates. Okay, so these 1,3 dicarbonyls are kind of signature functional groups for doing these reactions. So here I take a diester. This is called dimethyl malonate. It's malonic acid. Isn't there some sort of malonic acid thing in the citric acid cycle? I don't remember that. I'm trying to blot that out of my mind. You can have cyano groups that behave just like esters. They stabilize carbanions. You put 2 of them on there, that's more acidic than water. This anion, you can't just dump in water and protonate that. It's not basic enough. These are super stabilized carbanions. If you draw the resonance structures, the negative charge spends most of its time on the nitrogens or on the carbonyl oxygens. The negative charge is not really localized on the carbon, even though that's the main site for CC bond formation. I don't know why, but I've got this random minus charge here that's bothering the heck out of me. Let's get rid of that. I don't know what that was, some sort of pasting error. I apologize for that. And then over here, you can have mixtures of cyano groups and carbonyl substituents, and it makes that carbanion very stable but still nucleophilic. There's one more class of reagents that's very good at doing these conjugate addition reactions, these 1,4 addition reactions that you should have learned about in an introductory course, and that's dialkyl cuprate anions. So cuprate, 8, tells you there's a negative charge on copper. Cuprate, negative charge on copper. That means all the bonds to copper are nucleophilic. It's like tetrahydroaluminate. Aluminum minus, all the bonds to aluminum are nucleophilic. Palladate, negative charge on palladium, all the bonds to palladium. So it's the same idea. There's nothing special about that, but right, pay attention to those endings. When you hear something end in 8, it's telling you something about the chemical reactivity and where to start your arrows. So those are great for conjugate addition. Here's a couple more species that aren't maybe not as common. And another species that's very good at forming CC bonds are enamines. And enamines are nucleophilic on this end carbon. They're kind of like those stabilized enolates, right? If I push the arrows here, yeah, the lone pairs on nitrogen are nucleophilic, but they're donating into, gee, now what do? I feel like I have to finish the arrow pushing, so I'll draw that. Right, that yellow carbon there on the enamine, that's the site for bond formation. It's the end of the enamine. Draw a resonance structure, and it will tell you where you want to form a bond. On carbon, not on nitrogen. There's a couple of other atoms from lower rows that you'll commonly see adding to enones, not to the carbonyl of an enone, but to the end of an enone. And one of them would be this lone pair on phosphorus. Boy, we're down to lower rows. Generally, once you go to lower rows, you're going to tend to attack on this end carbon of an enone, not on the carbonyl. So selenium, sulfur, phosphorus, lower rows, big orbitals. The negative charge is not focused on a single atom, it's spread out. And so the same thing is what you would expect for sulfur. You would expect sulfur lone pairs to add to this end carbon of enones, not on the carbonyl oxygen. But in most cases, if this did add to the carbonyl, it would just get pushed right back out, so you can't tell. Yes?
So on the dialkyl cuprates, why are they more prone to doing that conjugate addition if, like, following like concepts kind of discussed earlier in the class, the longer bond relative to like inorganolithium or something, wouldn't that make it like more nucleophilic and more likely to?
Yeah, so the question is, why are like if I'm saying that the charge focused on a single atom is so important, how do we rationalize that dialkyl cuprates are giving conjugate addition and not addition to the carbonyl? And the answer is because we're not telling you truthfully what's the mechanism for addition of an enone. I don't really expect you to draw this mechanism, but when you have an enone, the first step is pi complex formation of the copper. It coordinates with the pi bond to make this intermediate that we're not going to draw. We're not going to talk about it. So it's because there's a secret mechanism that I'm not being honest about. But for now, if you have to, let me come back to this. But for now, if you have to push the arrows, just do this, right? Just do that. Forget about the secret mechanism thing for this class. When you get to an organometallic class or a graduate class, we'll be straight with you about what's going on. All right, but regular old nucleophiles like alkylithiums, where you have all this charge focused right here, the lithium is electropositive, the carbon here is electronegative, and so here you just add to carbonyls. Alkylithiums add to carbonyls. They don't add to that end carbon of the enone. Grignard reagents, they just add to carbonyls. There's nothing special about alkylithiums and enones. Most things add to carbonyls. So if you make the intermediate in this case, the intermediate would involve Just a simple alkoxide intermediate. There's nothing special here. Let me circle that so it doesn't look like a bond. So there's nothing special about just alkylithiums. So what are the reagents? Any alkylithium will add to the carbonyl faster. So you take an alkylithium and you add that to an enone, you're going to get addition to the carbonyl. Methyllithium, phenylithium, vinylithium, cyclohexenyl lithium, all the same kind of idea. Acetylide anions. So you should know that you can deprotonate alkynes that have a CH at the end of the alkyne to make acetylide anions. If you used that Smith textbook for organic chemistry, you spent like half a year where that was the only carbon nucleophile you knew about, so they used it for everything. It's not that common, but it will add to carbonyls just like alkylithiums do. Alkoxide anions will add to carbonyl groups faster than they add to enones. Boring, because that would just get pushed right back out. If you added to this carbonyl over here, the O- would just push that group right back out. It would not lead to anything useful for you. There is one class of reagents that is surprising to find in this list, and that is enolates. Sodium enolates, not very common, but lithium enolates. Not with two carbonyls, but where the carbanion is stabilized. Let me draw the other, another kind of depiction of these. Another way would be to draw it like this. I don't have room for that OET, and then put the negative charge here. Where there's only one carbonyl group, those add selectively to carbonyls. So if I took one of these very simple enolates, one of those types of enolates right there, and I added it to this enone system, you would expect that to add to the carbonyl. Not here, not there, but to the carbonyl group. And there's a special mechanism for addition of enolates to carbonyls. It goes through a 6-member transition state. We're not going to talk about that right now. There's other reasons why simple lithium enolates add to carbonyls. We just can't go into that right now. You just have, this one you can't rationalize based on charge, location, or delocalization. You have to take it on faith that those add to the carbonyl group of an enone, not to the end of an enone. Now, I've shown you everything here with methyl, vinyl, ketone. Right? There's a lot of other enone type systems that you can add to on what's called the beta carbon. So if I were to label this, I would label this carbon alpha, it's next to the carbonyl, and I would label it beta. So conjugate addition, 1,4 addition occurs at the beta position, and there's a lot of other reactive functional groups that look kind of like enones. So you can have an ester, same idea, you add to the beta carbon. So methyl vinyl ketone, you add to the beta carbon with these, not with methyllithium, but with those other reagents. So if you're doing conjugate addition, you can do it with acrylate esters, methyl methacrylate, that's ready to polymerize. Acrylonitrile, also ready to polymerize if you add to that beta position. That's how they make these nitrile gloves you wear in the lab. Cyclic enone, cyclohexenone, cyclopentenone, steroids like testosterone, cyclic enones you add to the beta carbon if you use 1,3-dicarbonyl compounds, phosphines, selenium anions, sulfur anions, all those soft anions where you don't have all this focused charge. And then, of course, if you added all these would add to the carbonyl group. All these things on this page add to the carbonyl. All right, so that's pi star. Boy, you should be familiar with adding to carbonyl groups. You should be familiar with alkylithium reactions, Grignard reagent additions to carbonyls. That's pretty standard stuff. Try to take advantage of those problems in the Smith textbook or whatever organic chemistry textbook that you used. Go back and practice those so you know addition to carbonyls. That shouldn't be controversial in an advanced class like this. Okay, but then there's these enone cases. Yeah.
I was just curious why you said that you only need a small amount of
Oh, somebody asked, like, why not 100 mole %? It would be fast. It would be even faster. It'd be 10 times faster here if we added 100 mole % DMAP, but it's expensive, so.
And the reason why you didn't use purine is because I use DMAP instead of purine is because you wanted a stronger base.
Well, it's not easy to get rid of pyridine. It's kind of a hard boiling solvent. Sometimes you end up with pyridine reactions. You have to extract it out with copper. You'll see some people keep these blue copper solutions on their bench top. That's to get rid of the pyridine when it's hard to get rid of pyridine as a solvent. So pyridine can be, it seems easy, but it's a pain in the rear sometimes to remove large volumes of pyridine and get rid of all the remaining pyridine. Okay, all right, so that's pi star. Mostly addition to carbonyls, but, iminium ions are important. Let me just make sure I got to the end of that for, was there one last, no, there was not one last slide. Okay, let's kind of switch gears in a big way away from adding to pi star. Pi star is that's where it's at. That's most of organic chemistry, most of biochemistry is adding to pi star. Adding to phosphoryl groups, that's DNA, RNA, kinase, protein kinases. Adding to carbonyl groups, that's making proteins, that's making peptides, making lipids. Citric acid cycle is all addition to carbonyls, if you had to memorize that pathetic thing in your biochem class. I want to come back to addition to sigma star. We already talked about addition to sigma star for proton transfers. But protons are a first row atom. That's easy. Let's switch to a little bit harder addition to sigma star where you drop down to lower rows, like if you're adding to carbon sigma star, or rows even lower than that. So, right, it's so fast to add to sigma star orbitals for protons. That's just acid base. But once we drop to these lower rows, this is not so fast. So let's go ahead and spend some time talking about addition to sigma star and get used to how to depict those mechanisms. Now, I hope I don't have to go into too much detail talking about just simple SN2 displacement reactions. This is unfortunately the first mechanism that people learn, and then they use it for 9 months like it's the only reaction they've ever learned about. So if you take a nucleophile, I hope you know that you add to sigma star when you've got good leaving groups like bromide, iodide, tosylate. Those are the common ones. But I want to talk about the transition state for this reaction. When you add to sigma star, there's an antibonding orbital. The antibonding orbital, sigma star, is sticking out on the back end of this carbon-bromine bond. The sigma star orbital is biggest here. So that's why you attack backside attack. Let's go ahead and draw out that transition state. In the transition state for sigma star, you get inversion of configuration if you have a stereogenic center there because you attack the backside. I'm going to draw a transition state here, and I'm going to be as careful as I can to try to draw this nice-looking trigonal bipyramidal transition state. A trigonal bipyramidal structure. This is the transition state for this particular SN2 displacement process. I've got the nucleophile sticking out here. In the transition state, this nucleophile is far away. That's a long, partially formed bond. The leaving group is leaving. I've got that Br minus there. That's a long, partially formed bond. Most nucleophiles are partially negative. Alkoxides, amines are electronegative, so there's, right, they're kind of bringing that negative charge to the closer to the amine. Leaving groups tend to be electronegative, so don't be surprised if your leaving group is leaving with a negative charge or building up more negative charge in the transition state. But it can't be all negative, right? We got to have some positive somewhere, and that positive charge is localized here on that carbon atom. So this is the transition state for an SN2 reaction. SN2 reactions go through this trigonal bipyramidal transition state because you prefer backside attack, and there is inversion of configuration if that carbon is a stereogenic center. So let me just write this down here. It's so important for you to understand the properties of trigonal bipyramidal structures. Bipyramidal. I feel like this might be something. It's been so long since I took freshman chemistry. Maybe they cover all this in freshman chemistry, and you guys already know about trigonal bipyramidal and the stereoelectronic properties of trigonal bipyramidal structures. So it doesn't matter whether it's a transition state in this case or a stable structure. They share some particular properties. Now, we're talking about SN2 reactions, and I just want to couch this in say something specific here, and that is that SN2 is not a great reaction. I realize it's the first thing they teach you. That's because the first mechanisms we understood at any level of detail from 1910 and 1905 were SN2. But that doesn't mean they have to teach you that first in organic chemistry classes, but that's the way they do it. So if you just take some simple nucleophile like hydroxide and an alkyl chloride, Yeah, you can make the alcohol by doing an SN2 displacement reaction. I mean, in this common case, this looks pretty simple, right? But that's not the major product of this reaction. The major product of this reaction is an E2 elimination. That's the dominant product. Now, sure, you could increase the yield, right? If it turns out that that alkene is quite volatile, you can easily evaporate that on a piece of laboratory equipment called a rotary evaporator and leave behind pure alcohol. If you wanted more of the alcohol or a higher yield, you just use a big excess of this, right? Throw in 10 equivalents of the hydroxide and your alkyl chloride. Who cares whether you're generating a ton of alkene you don't want? It may be forming twice as fast, the alkene you don't want, but at least you'll end up with a high yield of the alcohol. Now that works great, just adding excess alkyl chloride and excess hydroxide, unless you really think that the alkyl chloride is the expensive reagent, and it is. So if it took you 10 steps to make your alkyl chloride, you don't want to be using 10 equivalents of that and throwing it away. If somehow you had to pay for that alkyl chloride and it costs $4,000 a gram, some reagents do, you don't really want to be using 10 equivalents and wasting it forming the alkene. Because I'm sure it took a lot of work to make this carbon-chlorine bond somehow, and then throwing away that powerful bond to make an alkene is a waste of reagent. Okay, so SN2 isn't great, so we'll spend a little time talking about SN2, but really the important thing is to talk about other types of atoms. Okay, so SN2 reactions proceed through this trigonal bipyramidal transition state, but I mentioned the fact that because of this backside attack effect, you end up with electronegative atoms at the axial positions because of backside attack. But what's not so obvious is that you want the electropositive atoms to end up attached to the carbon if you're doing an SN2 reaction. That's where you want electropositive substituents. So again, it seems kind of obvious. This is where you want electronegative atoms here at the axial positions with those long bonds on the axial positions. This is preferred stereoelectronically. It's certainly preferred because the sigma star orbital is big on the back end. But if you make any trigonal bipyramidal structure, you want to have the electropositive. I don't know how to abbreviate electropositive. I don't want to write EP. I'll just write out electropositive substituents. You want electropositive substituents attached to that center atom. Otherwise, it's stereoelectronically unfavorable. It's higher in energy to go through transition states that have electropositive substituents attached to that central carbon atom. And let me show you a practical just way to think about how this has an impact. Here's an epoxide down below. And let's suppose I try to do a ring opening of that epoxide under acidic conditions. We've got alcohol in here. That epoxide isn't going to open just from alcohol. You've got to protonate it and turning it into a good leaving group. You can see they're adding catalytic sulfuric acid in there. And what's happening under these conditions is you're not forming a carbocation. You wouldn't know that. I'm telling you that to protonate that. And now the ethanol is opening that up. So and you can see that in the next intermediate over here, that you're protonating the O to make it a good leaving group. There's a ring strain in there that's assisting with this. And so now we can open up that epoxide. And which side do we open this epoxide on? The left or the right? On one side, we've got a trifluoromethyl group. On the other side, we've just got a regular methyl group. Don't be confused about the fluorine and its steric size. A fluorine atom is about the same size as a proton. The bonds are longer, but it's about the same size. Whatever I'm showing you here is not a steric effect. This is purely an electronic effect. I couldn't dig up a good example where the sterics were exactly equal on each side. It won't. Okay, so what's happening? You can see from the product, right? The ethoxy group ends up over here next to the CH3 methyl group, right? So you must have attacked on the side next to the methyl group. That was the preferential side for attack. Here, on the side of the methyl, and not on the side of the trifluoromethyl. You know, trifluoromethyl is very polar. Fluorine atoms have a lot more protons in the nucleus. You want to have electropositive atoms out here, not inductively electron withdrawing polar electronegative groups. You do not want electronegative groups out here in any good SN2 transition state. So if you have alkoxy substituents or fluorine substituents out here on this neighboring carbon somewhere nearby, it's going to make it harder to do SN2 reactions. So you'll see lots of examples of this. I'm picking kind of a dramatic effect with 3 fluorine atoms. You still would have seen regiochemistry if there was a single fluorine atom on there. Let's take a look at how you can slow down rates of substitution by having what if you put electronegative substituents on that carbon atom? Well, it's going to slow down SN2. So let's look at what happens if I'm trying to displace chloride down here, but I have more and more and more electronegative substituents on there. So if you add an extra chlorine on there, it is now slower. That one extra chlorine makes it slower to do SN2. Slow enough to where we commonly use dichloromethane as a solvent in the lab, and we don't worry about SN2 reactions at dichloromethane. They're not impossible, but that is way slower than trying to do an SN2 on methyl chloride. If you put 3 chlorine atoms, we don't worry about any SN2 on this solvent. It's called chloroform. We use that as a solvent, and we don't worry about doing SN2 reactions on chloroform. We used to use very commonly this solvent called carbon tetrachloride. That's the old-fashioned name. My dad said when he was a kid that they used to keep a bottle of that under the sink as a cleaning solvent for stuff. But it's carcinogenic, so people don't do that anymore, and we try not to use it in the lab anymore. But the general rates for SN2 substitution here are decreasing. When you put these electronegative atoms on that carbon that's undergoing substitution, it really slows down the rate of SN2 reactions. So if you want to generate a transition state, you want to have your electronegative atoms at the axial positions, the leaving group, the nucleophile. You do not want to have electronegative substituents on that central carbon atom that's undergoing substitution. Now that rule, that stereoelectronic rule, that you want electronegative atoms on the long axial positions, you don't want electronegative atoms on the central positions, applies to other structures. It's not just transition states. Yeah?
For the last slide, if the one with more chlorine is, because you were saying that was the fastest, but with the greater than sign seems better.
Did I do that wrong? The rates should be, oh, thank you for asking. I've got that totally backwards. Can I erase these? Sorry, you don't have a race on you. Maybe you do. You're exactly right. The rates, that's what I was saying here. The rates for this. Thank you. Boy, thank you for asking about that. Should be like this. That's a greater than symbol. Yeah, should be like that. The carbon tetrachloride, carbon tet, slowest of all. Yeah, you don't do SN2 substitution with carbon tet. At least I've never heard of it. All right. So this rule, electronegative substituents on the long axial bonds, that applies to all structures, not just transition states. So here's a siliconate intermediate or a siliconate species. These might be isolable. This came from a calculation that somebody did. You know, if you take these 2 siliconates, one with fluorides axial and the other with fluorides one axial, one equatorial, those are not the same in energy. Right? The one with the equatorial electronegative fluoride is higher in energy by 8.3 kcals per mole. How many times, factors of 10 more stable, is it to have axial fluoride there? It's more stable by how many factors of 10? See, you should be doing this in your head fast when I give you kcal numbers. Convert that to factors of 10, because that's what's logical. You know, that's the kind of thing we can think about. You know, I'm not good enough at dividing by 1.4. I can't do the math myself. So 10 to the 6, I'll trust you. So 1,000,000 times more stable, right? You don't want to attack with fluoride side-on attack, right? You would attack the opposite side of the leaving group, right? When you attack in SN2 transition states, you attack from the backside. You create a transition state that is stereoelectronically favorable. Now, you're going to see a lot of intermediates that involve trigonal bipyramidal structures, not transition states, but stable structures that you have to draw. You don't have to draw transition states unless I ask you to draw a transition state, but you do have to draw intermediates and steps in arrow-pushing reactions. So we're going to see plenty of reactions, I think, in this quarter where we add to phosphonium groups. So if I add a bromine to a phosphonium group, or you add a hydroxide to a phosphodiester bond in an enzyme, doesn't matter, right? You end up making a trigonal bipyramidal intermediate in those cases. So if you add in right? You're going to add opposite the most electronegative group. That's a stereoelectronic rule. Enzymes know that. Every enzyme we have ever looked at and determined the structure for, the nucleophile is designed and positioned to add opposite the most electronegative group, because otherwise you pay a stereoelectronic price that slows you down. If you have fluoride in a siliconate, you should have learned, or you probably learned, that you can deprotect silyl ether protecting groups by adding to TMS ethers using fluoride anion. And it makes this kind of an intermediate that we've got down here. So for phosphonium, you end up making this species called a phosphorane. You don't really need to know that right now, but that pentavalent phosphorus intermediate is called a phosphorane. This pentavalent intermediate here is called a siliconate. Notice that 8? That 8 tells you it's negative on silicon, and it tells you the bonds to silicon are nucleophilic. And then sulfur, same idea. If you have a sulfonium ion, oh my gosh, I'm missing a positive charge. Let me fix that. There should be a positive charge over here on sulfur, just like there was on that phosphonium. If you have a sulfurane cation like this, right, there is a stereoelectronic preference for the nucleophile to add not opposite the lone pair, but opposite the most electronegative atom. That's the preferred, and the sulfurane intermediate that you get, this is called a sulfurane intermediate, will end up with an equatorial lone pair. You don't want a lone pair to be axial. The lone pair is not electronegative. That doesn't make any sense. You can buy sulfur tetrafluoride from any chemical supplier will sell you sulfur tetrafluoride for pretty cheap. And when you substitute using sulfur tetrafluoride, step 1 is to lose one of those groups. And it's not the equatorial group that gets lost. It's the axial group that gets lost. Those bonds are longer, those bonds are weaker. Things leave from these types of intermediates from the same axial position that they started from. So when you add axial. When you leave axial. Here in the siliconate case, it would be the OR group that breaks, because that's the weaker, that's the easier group to push out. So this idea of understanding trigonal bipyramidal structures and transition states and this axial preference, if you're ever going to design a catalyst or an enzyme or understand how enzymes work, you have to obey these simple rules. There's no separate set of rules that you follow because something's occurring in an enzyme active site. So you can kind of see what's happening here. We're always adding to sigma star, but the key thing is that when you add to sigma star, in these cases, you don't break the bond like with carbon. Carbon, you can't have 5 bonds to carbon. That violates the octet rule. But sulfur, no problem. Phosphorus, no problem. Silicon, no problem. So in these cases, addition to sigma star doesn't break the bond on the opposite side. It weakens it. It lengthens the bond on the opposite side, but it still takes a second step to push out that leaving group from the opposite side. It's carbon where you can't have 5 bonds to carbon. So get ready to draw intermediates, these pentavalent 5-coordinate intermediates when you do substitutions at phosphorus, silicon. We won't see a lot of sulfonium chemistry in here, but if you do, it'll go through this 5-coordinate type of intermediate. I guess we'll see sulfonyl chloride substitution involve that. Okay, so now let's talk about silicon. We love making silyl ethers in organic chemistry. If you want to stop an OH from reacting, turn it to an O silicon, because you can make silyl ethers in 100% yield every time, and you can take those off in 100% yield every time. It's not like doing SN2 at carbon. Silicon ethers are easy to make in quantitative yield. And when you're done with that silicon ether and you want to get that thing off of there, you take advantage of the fact that fluoride loves silicon. Right? Hydrofluoric acid, it etches glassware because fluoride loves silicon. And so the mechanism for this, if you're to correctly draw this out, involves having fluoride, which just loves, did I mention fluoride loves silicon? Wow, fluoride loves silicon. Loves silicon. Man, let's go ahead and draw that out. Notice how careful I'm being not to break that silicon-oxygen bond yet. That's not the mechanism. You go through this trigonal bipyramidal intermediate with a negative charge on silicon. We're not messing with that stereogenic center. We haven't touched it. So you go through this pentavalent siliconate intermediate. If you cared about the geometry, usually we don't care about the geometry when we're just doing arrow pushing mechanisms, but if you did, the fluoride would come in from the backside. It weakens the silicon-oxygen bond when you do that, and so the next step of this reaction would be to have this come off and give the electrons to oxygen. In theory, you could push out the fluoride, but that's not the better leaving group here. And so let's go ahead and draw that out. And I'm not going to show the protonation step. When you buy commercial tetrabutyl ammonium fluoride, in fact, you can't get it dry. It always has water in there. They don't usually say that as a part of the reaction conditions, but there's water in commercially available. I keep wanting to call it T-bath. We call it T-bath in the lab because nobody wants to write all those positives and subscripts and superscripts, so we just call it T-bath. And then we end up with this, boy, look at that bond there between fluoride and silicon, fluorine and silicon. That's where it was headed the whole time. It was headed towards a fluorine-silicon bond. So that's the mechanism for deprotection of silicon. It involves a pentavalent silicon intermediate, so get used to that. You'll also see similar types of mechanisms when you're making silyl ethers. One of the most common silyl ethers that we make in the laboratory is a tert-butyl dimethylsilyl ether. Turns out that trimethylsilyl ethers hydrolyze off a little bit too quickly to be convenient. So that T-butyl group just adds a little bit of stability so you can chromatograph silyl ethers quite easily. I'm not going to show you the whole mechanism here for this reaction. Under typical conditions, you use a secret base that I'm not going to mention here that has a non-innocent role in the reaction. It's the nucleophilic catalyst role, like I showed you for DMAP, but I don't want to talk about that. So I'll give you a hypothetical base that's not a common set of conditions. If you just make a silyl ether, right, the expected mechanism, if I'm just telling you base and not the identity of that, would be to have this lone pair on the oxygen attack the silicon. Don't break that silicon-chlorine bond. That doesn't happen in the first step. You're going to go through this intermediate here where we have, I'm just going to abbreviate this whole alkyl thing as R. And I think I'm going to need to deprotonate that OH, so let me be clever here. Let me be smart about this and draw that bond, because my next step is to deprotonate that H. So we'll have this oxonium ion bound to silicon. And we have our chloride leaving group. That bond to chlorine is weakened. Now before I push out that chloride, and there's a negative charge on silicon, it's a siliconate. Before I push out that leaving group, I'm going to deprotonate the alcohol. Deprotonate the alcohol first, the OH first. Then we can talk about. So the conditions, if I've got a base in there, the conditions are going to be basic. So I'll use the symbol B. It's not wrong if you used A minus, but I usually try to pay attention to that. And so now we end up with this simple trigonal bipyramidal intermediate, ready to push out the chlorine. And when you're typically drawing mechanisms, you're not really going to be drawing trigonal you'll probably draw it like this, right? In most cases, we don't care that it's trigonal bipyramidal. We just want to draw it that there's 5 bonds to silicon. There they are. And let's just push that out. And that's the mechanism. Don't substitute it silicon in one-step mechanisms. Don't pop off the chloride leaving group to make a selenium cation. You don't make things that look like carbocations with silicon. Right? There's this obscure area of chemistry having the leaving group leave from silicon. You're not going to see that. Okay, so when we come back, we'll talk about more silicon substitution reactions, such an important type of functional group for modern organic chemistry. More addition to sigma star.